Good morning, everybody, and welcome to the 7th edition of Diderot Mathematical Forum. It's Antonio Gomez Corral, and I am jointly with Miguel Ángel, the organizers in Madrid of this edition of Diderot Mathematical Forum. The cycle of conferences Diderot Mathematical Forum produced by the European Mathematical Society in 1996. Each conference takes place simultaneously in 3 European cities, exchanging information by means of video conferences. The talk deal with a specific topic, and they have both a research and a public component. In this edition, the locations, the European cities, are Paris, Milan, and Madrid. The topic is biomedical applications of mathematics, and the event is organized and coordinated by the Raising Public Awareness Committee of the European Mathematical Society. The forum is organized in 2 sessions, 1 session in the morning and 1 session in the afternoon. In particular, 3 plenary talks take place today in the afternoon. The first plenary talk will be transmitted from Paris, the second one from this room in Madrid, and the third one from Milan. The session in the morning here in Madrid, the session we are starting right now, consists of 4 talks about the interplay between mathematics and biomedical problems. Regardless of the session, if you are watching a talk on your computer, but you are not here, you are not in this room, you may also ask a question to the speaker by using the Twitter account that is available in the webpage of the European Mathematical Society. The details can be found in the webpage of the Society, just over the link you are using to follow from Madrid. That's all. Our first speaker in this session is Juan Carlos Nuño from Universidad Politécnica. He is going to review some evolutionary models in random environments. Well, Juan Carlos, thank you very much for accepting the invitation. Thank you.
First of all, I wish to thank the organizer of the Diderot Mathematical Forum 2016, in particular Antonio Gomez and Miguel Ángel Herrero, for allowing me to give this talk about evolutionary models in variable environments. I also thank you for coming and all the audience that is in internet. The Russian biologist Theodosius Khovansky published in 1973 the essay, "Nothing in biology makes sense except in the light of evolution," and opened a new era of debate about the role of evolution in biology. But that's a bit of a tricky statement, because what is evolution at all? This is a fundamental question that many natural scientists are asking for a long time. Is this the result of biological evolution? Certainly it is not, although cultural evolution can be used to explain the differences between these 2 masterpieces. In common language, one could say that nothing makes sense in the light of evolution, but this talk is focused on biological evolution, in short, evolution. At the times of Khovansky, the origin of life was a central issue of the investigation of several scientists. In particular, James Lovelock started to assess the role of the planet Earth to sustain life and the probability of finding other life forms in extraterrestrial planets. Just in the same decade, Lovelock presented his hypothesis of Gaia, where a close relationship between life and its environment is postulated. The important point here is that the interaction is not only from the environment to life forms, imposing constraints to the biological evolution, but also from life to the environment, modifying its state. So inducing these changes in the environment, life is changing its own conditions for evolution. An essential conclusion that can be derived from these studies is that life forms, as we know them at present, are the result of a deep interaction between biological and environmental processes. As some scientists do not hesitate to state that the stability of life on Earth is caused by the homeostasis that assures that life itself brought about the optimal conditions for its appearance and permanence. However, it is important to point out that despite this interaction between life and Earth, it is estimated that 99.5% of all species that ever lived had gone extinct, and that the typical existence time span of a species is around 10 million years, which is like 3 minutes in a 24-hour day when compared with the history of the Earth. This means that it's not always beneficial, that this interaction is not always beneficial for all species. In contrast, the modification of environmental conditions could be disastrous for some species, even for humans, the most evolved of all the species ever known. As a matter of fact, for the first time in history, we were aware that human activity is changing the Earth, our natural environment, and we wonder whether adaptation to these new conditions will be possible. This concern is so important that one could say that nothing in evolution makes sense in the light of its environment, except in the light of its environment. Consequently, mathematical models of evolution should take into account necessarily this aspect. Eco-evolutionary models are building the bridges between classical theories of biology and ecology. They consider, besides the classical ingredients of evolution, the ecological interactions among species and between them and the environment. Population dynamics is the natural framework where the laws of biological evolution appear. This talk will apply an approach based on differential equations to describe the change of the population over time and space. This approximation is strictly valid when the population is large enough and it is homogeneously distributed in space. The three essential factors that are operating in biological evolution are replication, that is the capability of individuals of making copies of themselves, mutation, the capability of producing individuals of other species, and a consequence of them, selection, the capability of interacting of individuals. Let us briefly review the basis of mathematical modeling of these mechanisms. Replication is the natural mechanism to make copies of individuals. Under ideal conditions, pure replication without mutation and absolute isolation from the environment, the per capita time derivative of the population is constant. This is a straightforward consequence of the balance between birth and death. R, the parameter R, is just alpha minus D, the growth rate minus death rate. The solution, as you all know, of this initial value of the initial volume problem associated with this equation is this, or has this exponential form. And depending on the sign of the R, the population will tend to infinity or will tend to 0 when R is less than 0. This is known as the exponential law or Malthus law. It is important to remark that despite the unrealistic nature of the unbounded solutions, the exponential model can be taken as a basic model when no external forces are acting. In this sense, as Tarchin pointed out, exponential growth can be considered as the inertial law of population dynamics. In general, the derivative per capita of the population is a function of other factors, in particular those that are consequence of the limitations imposed by the environment. Limitations due to finiteness of natural resources can affect the growth rate or the death rate over both. In the logistics, also referred as the Berthus model, the dependence with the density affect both, as is shown here in the slide. Whereas in the Carter-Prince model, the density only affects the growth rate, whereas the death rate remains constant. Here, omega is the carrying capacity of the system. The main difference with respect to the logistic model is the existence of an equilibrium point of extinction. Mutation is the natural mechanism to bring about new species that either can be integrated in the population, at least during a certain period of time, or removed due to their low viability. Mutation can be regarded as a stochastic process that generates a flow of individual among species, already present in the population or not, that can be incorporated into the equation of evolution in different ways. When the species do not interact, catalytically at least, the dynamics of the population is described by the replicator-mutator differential equation that you see in the slide. It accounts for mutation that produce individuals of other species from individuals of species K, this is the first term of the right-hand side, and for mutation that give rise to individuals of any other from individuals of any other species into individuals of species K, the sum in the second term in the right-hand side. The last term represents the death rate, as we commented before. Here, L is the number of different species that are present in the population. Depending on the choice of the growth rate, we obtain either the Eigen's model or the logistic, or also called Carter or Carter-Prince model. Note that, strictly speaking, the species interact by mutation, and that the environment is constrained if the logistic model is applied. In contrast to the error-free case, an equilibrium population can exist where the master sequence is surrounded by its nearest mutants. However, this equilibrium distribution, the so-called quasi-species, is dynamic in the sense that new mutants are continuously appearing, and one of the major results derived from this model is the existence of error thresholds below which the quasi-species is stable. A particular model that allows to calculate these error thresholds is the so-called error tail model that considers only two species, one of them being the master species and the other the error tail formed by all the mutants of the master. If we assume that there are no back mutations, that is, no individuals of the master sequence appear as mutants of the error tail, the system of differential equation reads as shown in the slide. Here, for simplicity, we have assumed that the death rates are both equals. Three equilibrium points appear. The extinction, this means no population of either of the species. The error catastrophe, where the master copy is absent, only remains the error tail, and the state of coexistence, the quasi-species. As can be seen in the bifurcation diagrams, if D is larger than alpha E, this means that the replication of the death rate of error tail is larger than the rate of replication, there is an extinction threshold, a critical mutation rate about which the whole population disappears. This is reflected here. This is the mutation rate. This is the equilibrium population of the error tail, and the below QX, the population disappears. When the D is larger than alpha E, a new threshold appears that is calculated as the ratio between the growth rate of the error tail and the growth rate of the master sequence that separate the two states of two situations, one in which the coexistence exists above this error threshold, and below what we obtain is the error catastrophe. That means the loss of information that was in the master sequence. Selection results as a consequence of error-prone self-replication under a specific environment. It is the big challenge of theory of evolution, to predict the outcome of selection given the conditions, both biotic and abiotic, under which the population evolves. Only in very simple toy model is it possible to understand how selection works. For instance, when the growth rate of individuals is constant and the population of each changes over time exponentially, the species that had the largest growth rate will take over the population. This one very easy result that explains what is selection, or what is the meaning of selection, and also present the difficulties of understand or the obtain the outcome of selection. As we have discussed before, in order to have a complete and rigorous description of evolution, we need to take into consideration the environment. This fact is especially relevant when the time scales of the variation of the population and the environment become comparable. The consideration of this influence into the previous simple mathematical models requires to answer at least 3 questions. First, how does environment interact with the population? As we have already seen, this influence can be either unidirectional, from the environment to the population caused by the purely abiotic variations, as for instance, climate change and physicochemical alteration of the media, or bidirectional, when the population also affects its environment and likely a feedback appears. Secondly, how do we take something.
It's fine. Sorry. Okay.
Okay. Oh. I'm sorry. Maybe I will use this one. I'm very sorry. Secondly, how do we take into account environmental changes? Mathematical models usually take into account environmental changes in the dependence of the model parameters. We assume for simplicity that the environment state can be completely described by only one parameter, that we will refer as its temperature. A first possibility is to consider that the thickness of the species depends on the temperature, that in turn is a function of time. Another possibility, although less studied, is to suppose that the mutation rate depends on the environmental temperature. In the particular models we are working with, we assume that the growth rate of each species depends on the external temperature as a Gaussian concentrated at an optimal temperature Tk of growth. Besides, it is multiplied by a logistic term for the population to be bounded by a global carrying capacity. The third question is about how the population modifies the environmental conditions and in turn also influences the state of the population. The model we're applying to study this bidirectional interaction considers an additional differential equation that describes the time evolution of the environmental temperature. Here, lambda J are parameters that represent the strength of the influence of species J to modify the environment. Beta is a non-negative parameter, and psi t is a noise that in particular could be assumed to be a Gaussian white noise with zero mean. If mutation doesn't exist, the change over time of the population of each of the species is written in terms of the following differential equation. Here, alpha, the influence of the temperature here appears in this growth rate. We have applied this model to explore the effect on the population of a variable environment temperature in some simple situations. A third result we have obtained is that the external noise can prevent extinction. This is an example of one species that in the deterministic case, when noise is not present, dies out and that it survives when the temperature changes randomly. The figure in the left top corner of the slide depicts the deterministic trajectory of the population that approaches to zero as time tends to infinity. On the contrary, on the right, we see that when noise is active, the population oscillates around an average value, around 1,000, and you see here also that the noisy temperature, the temperature is oscillating around 0. A second example shows that noise can induce coexistence. As before, we assumed that the environmental temperature changes randomly as a result of the addition of a Gaussian white noise with 0 mean, and now with variance 2. In the left top figure, we see how the trajectories of the populations go to 0 in the absence of noise, and on the right, how the presence of the noise stabilizes the population and enables the coexistence of both species. As before, the temperature oscillates around the deterministic mean, and as it is shown in the right bottom corner. A third result I want to show concerns how the capability of changing the environment can modify the evolutionary properties of the population. To show this, we use a similar error tail model as I presented before, but now the error tail is able to modify the external temperature, and therefore the thickness of the master species. Importantly, each species has a specific optimal temperature that allows them to respond differently to the environment. As we see, the system is nonlinear and prevents to obtain analytical solutions. However, we can solve it numerically, and as is presented in the next slide. The important result here is that the Q thresholds are modified by the action of the mutants. On the one hand, the extinction threshold rises with respect to the quasi-species error train model, and this increase depends only on the optimal temperature of the master sequence. It is reflected in here in this term. On the other hand, the modification of the error threshold depends on the optimal temperature of both species. Only when both temperatures, optimal temperatures, are equal, we recover the error threshold of the classical quasi-species model, error train model. Well, as we have briefly discussed in this talk, it seems evident that nothing in evolution makes sense except in the light of its environment. I think that the importance of the environment is greatly reflected in this School of Athens fresco by Raphael, where the classical geniuses are surrounded by perfection. It seems clearly that for the artist, this perfect environment is geometric. And we all know that geometry reveals the secrets of nature. So one is tempted to rephrase again the famous sentence of Theodosius Sovansky and conclude that nothing in biology makes sense except in the light of mathematics. Thank you very much.
Well, thank you, Juan Carlos, for this nice talk. And well, it's time for questions. So the first question, please. Well, so I have a question for you, because you have been talking about evolution, but I wonder if similar rules of evolution can be found, for example, in social sciences.
Yes, sure. Yes, this is a great relevance, have a great relevance in other fields. If you are thinking about, for instance, public opinion, you see that the formation of public opinion follows similar rules as we have described by now for a biological system. Public opinion is formed by the opinions of individuals, but public opinion is affecting the opinions of individuals. So in this system, you also have a feedback between the influence of individuals in public opinion, and this average opinion of the society is also affecting the individual, the opinion of the individuals. So it's a feedback that is evolving with rules that at the moment are not well known. As a matter of fact, this system is also affected by other external inputs that can modify abruptly the public opinion and by influence the opinion of all the citizens, and the way the society is adapting to these changes is a matter of study now at present by sociologists. Of course, we can apply the same techniques and we can also conclude similar results.
Well, thank you. Question. Sorry. Just a second. Sorry. Just a second.
Do these models apply to Facebooks or any social networks?
Yeah, sure. This is the same. It is a social system that is following similar rules, because in this kind of social networks, suddenly appears some information that start to spread and can influence the opinions or the way the other members of the society behaves. But the behavior of these individuals is also affecting the way the spreading of this information that have entered in the network, affecting the way this network or this information is spreading. So it's the same kind of system. I don't know the rules, because as you have seen in this presentation, depending on the hypothesis you are using or you are applying in your model, the behavior is very different. So the great difficulty of this kind of models is the complexity of the response depending on the boundary and initial conditions. There are very nonlinear models that are very dependent of these conditions and the value of the dependence of the parameters. So it seems that we know what is the important to in this system, but we don't know how to handle these changes of these variations.
Oh yes, my question was more or less in that direction. How do you know when it's reasonable to add, for instance, noise, or when it's not? Because you said that in some instances you get extinction or whatever, and in others, if you add noise, you don't. So how do you know when one applies and the other one doesn't?
In principle, in all cases, noise must be present, because environmental changes are noisy. The problem in this case of this kind of approaches is that you have to simplify the problem. And sometimes what you do is to start with the simplest model and to add different elements. It is practically impossible, as I told you, to solve the general problem with a field landscape, a general field landscape with the influence of an external environment that is randomly changing, and it is also affected by the population. So you cannot solve completely the general model. So you have to, what I have shown you, is that when you have the deterministic case and you can solve it, it changes the behavior of this system, of this simplest system, change when you add the environment. When you take into consideration the environment, you change the outcome of the deterministic model. So what you are simply concluding is that these elements are very important to be taken into account in your model. But of course, you should include everything in your model. But the problem is that maybe this hide the pure aspect of the relevant aspects you want to study.
So I have a question. So how difficult is to put numbers in your parameters?
To put numbers?
Numbers, yeah. How do you estimate the parameters in your model?
Well, it's difficult. Yeah. It's also difficult because you are talking about progress in evolution in very different time scales, and you are more or less qualitatively comparing what is about when the environment is changing and when it's not. but you cannot compare the time scales. So it's difficult to calibrate all the parameters. So this is, as a matter of fact, in this kind of problems in evolutionary time, there are no experimental data, let's say. So you are speculating about how evolution have worked in these times. Yes. But in any case, people working in these kind of problems, when they are what they call system biology, are cultivating population of bacteria, and in these experimental devices, you can calibrate better the models. So all these eco-evolutionary models are now being applied in system biology. Because in bacteria, in the evolution of population of bacteria, you are obtaining or you are playing with the same ingredients of evolution, but in a very short period of time. So this, I think, is one of the more interesting fields now in science, in biological sciences.
Well, thank you very much, and well, let's thank again to the speaker talk.
Thank you.
Well, just a couple of seconds in order to prepare the second presentation.